we start with the tracking problem in state feedback design. In this we will study introduction to tracking problem in state feedback design, then design of state feedback controller considering steady state tracking, and numerical example. Now about the introduction to tracking problem in state feedback design. If you see any system, for that system there is need to design a controller. So what is the basic purpose of controller is to clear the transient issues as well as the steady state issues. Now we have seen state feedback control design, and we have seen that for state feedback design, that is for x dot equal to ax plus bu, y equal to say cx, the controller kc is determined as 0 0 0 1, a controllability inverse phi of a, and here this controllability matrix QC is represented by B A B a raised to n minus 1 b. So, you will find that the controller in a state feedback design is depends upon B matrix, A matrix, and phi of A is the desired characteristic equations. Now, we will find that there is no role of C matrix. C is the output matrix. So, whatever the things in the output, it is not play important role in a controller design. It means that there can be some issues. Now, here this issues is respect to steady state error. It is because if you write any transfer function g of s equal to s plus 2 s square plus 3s plus 1. So, this is a transfer function. Now, the state space model of the system is given as 0 1 minus 1 minus 3, and B matrix is 0 1 and C matrix is a 2 1. So, here we will find that A, B, C is there, and if you find out the steady state output by using final value theorem, it is given as limit t tend to infinity of y of t equal to limit s tend to 0 of s g of s into say r of s. Now, here if you see limit s tend to 0, s g s is s plus 2 divided by s square plus 3s plus 1, and r s is for step input, this r s is 1 by s. So, here s and s will cancelled, and we will find that replacing s 0, that is 2 by 1. Now, here we will find that the steady state output for this plant is depend upon this matrix, that is we will get 2 by 1, that is gives 2. Suppose instead of this s plus 2, let us say there is say s plus 1 s square plus 3s plus 1. So, in that case your steady state is 1, this is 1. That means the steady state is depends upon the C matrix, and here we have not taken care of the C matrix. Now, again see here, now we take one transfer function as 1 by s square plus s plus 9. This is the transfer function. Now, here we apply input r of s and output y of s. we want to take the step response of the system, and the step response of the system for this plant is given as like this. There is some oscillatory behavior and there is some steady state value. Now, the steady state of this is 0.11. But suppose if you want a steady state of 1, that means that here we have to design a controller. Now, what we do? We develop the state space model of this plant. The state space model of the plant is given as x dot equal to ax plus bu, y equal to cx, and here is A matrix is 0 1 minus 9 minus 1, B matrix as 0 1 and C matrix as 1 0. Now, for this system 1 upon s square plus s plus 9, we have determined its response. See, here this is response, and then we have also developed the state space model of this plant. Now, here we will find that there is a oscillatory behavior. Now, our purpose is to design the controller for this system. So, controller means we have to design the KC. So, here the controller KC is given as 0 1, then controllability matrix inverse into phi of A. Phi of A conserve with the desired poles. So, here our desired poles are at say minus 1, minus 2, and now here KC is given as 0 1 and here B AB inverse, and here this phi of A. So, how to get the phi of A? So, this phi of A is depend upon this characteristic equation for this. So, s square plus 3s plus 2, and now corresponding this phi of A equal to a square plus 3a plus 2. So, here the controllability matrix QC is B AB and it is given as 0 1 as B is 0 1, and this AB you will get as 1 minus 1, and if you make the QC inverse of the same, we will get 1 1 1 0, and this phi of A equal to as a square plus 3a plus 2i, and here if you replace the a as 0 1 minus 9 minus 1 multiplied by 0 1 minus 9 minus 1 plus 3 0 1 minus 9 minus 1 plus 2 0 0 2. So, after solving you will get minus 7 2 minus 18 minus 9, and therefore, the final controller KC is given as 0 1, QC inverse is 1 1 1 0, and here minus 7 2 minus 18 minus 9. Now, if you multiply this by this, so after this you will get 1 0, and here we will get minus 7 2 minus 18 minus 9, and here multiplication by this you will get minus 7 2. Now, for this particular plant, that is x dot equals to ax plus bu, y equals to cx, ABC we know, then we have desired poles minus 1 and minus 2, and by means of Ackermann's formula, this is Ackermann formula, we have got the controller KC. Now, when the controller will come into picture, what will be the its closed loop system or the closed loop transfer function, and we have to see the response of that closed loop transfer function. So, here as x dot equal to ax plus bu and as u equal to minus kc x plus r, and here we can get a minus into x plus b into r, and if you solve it we will get 0 1 minus 9 minus 1 0 0 minus 7 2 plus b, this is 0 1 into r, and after solving this you will get 0 1 minus 2 minus 3, this is x plus 0 1 into r, and output y is Cx, so it is 1 0 into x. So, we will find that by considering the controller in a system, we have got the state space model in this form x dot equal to a minus bkx plus b into r and y equal to Cx. Now, we will find that this particular system, it is in a companion form 0 1 minus 2 minus 3, and here 0 1 C 1 0. So, from these equations we can directly write down a transfer function as GCL of S, that is closed loop transfer function. So, the numerator it depends upon say C, so here is 1, and the denominator it depends upon this. So, here we can write down as s square plus 3s plus 2. Now, this is the closed loop transfer function, and if you determine the response of the system, so response as we have placed the poles here minus 1 minus 2, that means system is of overdamped nature, but about the steady state. So, here steady state for this plant for step input is 0.5. So, it is 1 by 2, that is 0.5, and response is like this. So, 1 by 2 like this, but our reference is 1, but output will got 1 by 2, that means there is a steady state error, and therefore, by means of state feedback design we cannot say that we have got a desired result, because the desired results depends upon transient issues as well as steady state. Transient issues we have solved because of minus 1 minus 2 they are pole placed, but there is an issue with the transients, that is the issue with respect to steady state, because steady state is 1 by 2 and 0.5, but our requirement is that steady state that is equal to say 1. This is our requirement. Now, how to solve this problem? Now, our main purpose is to solve this problem, and now we will see how to solve this problem. So, here we are taking the plant as same x dot equal to ax plus bu and y equal to Cx. Now, we develop the block diagram for this plant. So, we have a summing block, and here is one integrator, then we have output say C, and here is y, and here is state x, because of integrator it is x dot. Now, this x dot equal to ax and here is this is B and here is U. So, here x dot equal to Ax plus Bu and y equals to Cx. Now, our control law is that is U that is equal to minus Kcx plus R. Now, here this is U. So, this U here this is a control law. Now, here is a reference input R and here is a controller Kcx plus R. So, base this is the control law, this is state space equations, and now we have got this diagram. Now, here is the problem about the output y. Whenever we get the output, there is an issue with the steady state. That means, although we are controlling the states, we are getting the good transient phenomena or transients have been improved, but there is a problem with the steady state. Now, how to make the arrangement? Now, the arrangement which we are going to make like this. Now, we will design a control law in such a manner that suppose if you take U equal to minus Kx plus y, Kx plus R, this is the original as per this logic. Suppose here if you write the control law as U equal to minus Kx plus this small Ts a constant value multiplied by R, where R is the R belong to the reference input and Ts which is to be computed in order to reduce the steady state error, that is the Ts is computed to ensure the steady state error. That means the Ts we have to design such manner that the error to be 0. Therefore, now here control law has been changed like this, that is here R you can add one block of Ts, and now here we will find that here this your control law has been changed to U equals to minus Kcx plus this Ts into R. So, this is a Ts is a constant which helps in reducing the steady state error. Now, we will see mathematically how this Ts helps in reducing the steady state error. So, now here x dot equal to Ax plus Bu, and now here Ax plus B, U will write as Kx plus this Ts into R. Now, here equation has changed to A minus Bkx plus B into Ts into R. Now, this equation we have determined. Now, what is the steady state? Steady state is nothing but equilibrium point. So, it is a constant. So, the derivative of any constant becomes 0. Therefore, what we have now here steady state xs dot that is equal to 0. That is the condition for steady state. Now, here we write the equation as xs dot A minus Bk xss plus this controller, which controller is Kc B into Ts into R. Now, here controller is Kc, A minus Bkc, Kss plus B into Ts into R. Now, our main performance is that at steady state this is equal to 0. So, this equation can be written as A minus B into Kc xss plus B into Ts into R. Now we have to solve this equation and see the result. So we can write 0 minus A minus B into Kc XSS plus B into Ts into R. Now here XSS steady state we can write down as A minus B into Kc inverse into B into Ts into R, and now here output YSS equal to CXSS. So we can write down as minus C A minus B to Kc inverse B into Ts into R. Now here is the steady state output. Now in the steady state output we have C A minus B Kc inverse B into Ts into R. If you see, if there is no Ts, the equation is in this equation, that equation there will be no Ts. Now we have got YSS. Now about the steady state error, the steady state error is given as reference R minus steady state output, that is YSS. So now we replace the value of this here, we can write down as R plus C A minus BKC inverse B into Ts into R. Now take R common, 1 plus C A minus BKC inverse B into Ts. Now what we want? What we want, that the steady state error must be equal to 0. So when this is possible? So this is possible if this equal to minus 1. So if this is equal to minus 1, this equation is there, that is called steady state error, and what we want, that we want that this particular error to be 0. So this is possible when these particular equations which we have written, that should be minus 1. That means your equation should be R plus 1 minus 1. If it is there, that means your error is 0, that means this equal to minus 1. So we can write down as C A minus BKC inverse B into Ts equal to minus 1, and now here we write minus 1, but here the C A AB and here all these parameters which are known and that cannot change, the change we can do here in the Ts. That means we have to design Ts in a such a manner that makes steady state error 0. That means your result is minus 1 divided by C A minus BKC inverse into B. So this is the compensating factor for steady state error, that is the Ts. So this Ts we have to arrange here. So if we make the arrangement of Ts here, we will find that error will be 0. Now what we do in order to see whether the result or the mathematics we derived is matches with the desired result or not, for that purpose we will take an example which we have taken earlier and we see the result. So this Ts equal to minus 1 divided by C A minus BK inverse into B. Now this is the Ts. Now we calculate these factors, that is C A minus BK inverse into B. Now we see A minus BK earlier. So A minus BK is 0 1 minus 2 minus 3. So here as we are going for same problem, C is 1 0, and here we will write down as 0 1 minus 2 minus 3, this is inverse into b, and here it is equal to, if you solve it, because here b is here 0 1. So, if you multiply this and this will come up minus 1 by 2, and here if you put it here in this Ts, we will get this Ts as 2. So, now for the problem which we have taken, here we have got additional parameter Ts, therefore, now our equation is x dot equal to a minus bk into x plus b Ts into r. Now, here our a minus bk is 0 1 minus 2 minus 3x plus, so b is 0 1 and because of Ts is 2, so we can write down as 0 into 2 into r, and therefore, here if you solve this, that is x dot equal to a minus bkx 0 1 minus 2 3 r plus 0 2 into r, and now if you solve it, we will find that the equation for this is 2 upon a square plus 3s plus 2, that is the modified transfer functions, that is this is called as g modified CL of s, and here basically for this problem y equal to 1 0, and therefore, the transfer function for this type of model equals 2 divided by s square plus 3s plus 2. Now, if want to determine the steady state error, so steady state error means limit t tend to infinity of y of t equal to limit s tend to 0 of s into g m CL of s into step input Rs, and here we will find that limit s tend to 0 of s divided by 2 upon s square plus 3s plus 2 into Rs is 1 by s. So, this is cancelled, and now here replacing s 0 we will get 1. So, steady state 1 we have got, the steady state output is 1, error is 0, and therefore, whatever is the required results that is satisfied, that means in this case the response of this system, let us say t, say y of t will get steady state of 1, this is 1. So, you will find that because of the additional parameter Ts in this plant, we have got the steady state error 0, and that means output has reached properly to steady state, that means the output tracked the reference input. So, this was not possible because of the conventional state feedback. So, because of this is possible. So, we can use this type of results for different problems. Now, here I have solved an example, you can solve as many examples as possible, and let us see whether this methodology has satisfied the steady state error or not. Now, references for this is Ogata, then this is Stepney et al. Thank you.